true. Okay, this must be true. Because I just use the lowering property of this to get the first one, and then use the raising operator of this to get the second one. But this must be equal to n psi n, because this is a number operator. Okay, number operator operating on a number state. Just give me this one. But then Bn and An are complex conjugation of each other. So this is An squared. Okay? So I have An squared. An magnitude squared must be equal to n, which means that An must be square root of n. Okay? Bn must also be square root of n. Both of them are square root of n. Of course, you can say that you can add an arbitrary phase to it, because this is magnitude squared. You can add a phase to An, but that doesn't matter, because you can always absorb the definition of the phase into the annihilation and creation operator. Okay, because the An and Bn are defined over here. An is defined over here. If there's a phase vector, you can always put it into there. And Bn is defined over here. If there's a new phase vector, you can always put it to that thing over there. Okay, so let's define it to be a real number to make life simple. An is a real number as such. So you have the property of the raising and lowering operators well defined, and now you have this lowering operator operating on a number state just root n times the number state lowered by 1. And then A dagger, okay, operating on the number state is just n plus 1 psi n plus 1. Okay? So these are very important properties. These are very important properties, and you should remember them. And then we can now find the entire eigensolutions of those equations. This equation by using the lowering and raising operator approach. Okay, lowering and raising operator approach. And we say that if you have a ground state, if this is a ground state, okay, it will have the property that if you try to lower it further, it will give rise to 0. Okay, it will give rise to 0. But what was A hat? A hat is just equal to 1 over root 2 d equals c plus the c. So if I write this thing in coordinate space explicitly, it's just this equation over there. Okay? So you can actually find the ground state eigenfunction in coordinate space quite readily. And you can prove that this is the solution e to the minus c squared over 2. Okay? It's a Gaussian. It's a simple Gaussian. So the ground state of the quantum harmonic oscillator looks something just like that. A Gaussian function. Okay, the Gaussian function looks just like that. And in order to find the next one, we just use the raising operator. Okay, you use the raising operator to find the next one. And you can keep raising and raising and found all the eigenstates. Because you know the ground state ones. Okay? And you can define any number state to be 1 over root n factorial A dagger to the n multiplying by the ground state. Because every time when you raise it by 1, you introduce a root n plus 1, and if you go through that, you actually have to divide by root n plus 1 every time when you raise it in order to make this a normalized function. Okay, in this one shot, we write down all the number states exactly, and there's no approximation being made here. Okay, are there any questions regarding this? Okay. So, these are some very important properties of the quantum harmonic oscillator. And what it says is that the energy levels are quantized in this manner. You can also use this to prove that all the eigenstates have this energy level. Okay, you can start with the ground state and look for the eigen values. They will all have these values. Okay, because of this property, and they're self-consistent with each other. Okay. So what happens is this: we have a quantum harmonic oscillator now. You can think of this as the amplitude, and A hat A as being some kind of an amplitude. A dagger A is some kind of a number operator that's related to the number of they like to say use the word photons, okay, but sometimes it's rather confusing to call this states photons at this point, okay. But some books would like to call this photons, the number of photons that you have. But I would like to say that it's just a number of packets of energy that you have at this point. Okay, not to confuse yourself with photons at this point, because we haven't reached the photon stage yet. Okay. In the quantum harmonic oscillators, you will have all this quantization of energy levels, and the energy levels are uniformly spaced. Okay. So what happens is this, that if you have these quantum harmonic oscillators, say sitting next to each other, I just draw a classical picture here, but let's assume that you're sitting next to each other. Something like this. And they're coupled to each other by some forces. It could be van der Waals forces or some kind of atomic forces between them. And classically, we have this picture of a linear atomic chain. And then classically, we know that we can send a wave down this linear atomic chain. Right? You can, like if you have a piece of rope, you can send a wave down the piece of rope. So we can send a waveform down this linear atomic chain in the classical picture. Okay. Then the wave will displace this classical harmonic oscillators, and they will move back and forth, and they will send a wave down. But what happens is that these classical harmonic oscillators will have to be replaced by quantum harmonic oscillators if you want a quantum picture of this wave propagating down the atomic chain. Okay? And we will have to think of this as being the quantum harmonic oscillator. And it will carry a wave down the chain. And that wave, because they are a consequence of the oscillations of this harmonic oscillator, they will have to have quantized energy values as a propagator. They will have to have quantized energy levels. And for a structure like this, which is mechanical, those quantized energy levels are known as phonons. Okay, known as phonons. But what happens for the electromagnetic case? The electromagnetic case is more interesting. You can think of electromagnetic signal as being something very similar to this picture as well, except that it's a little bit more complicated. Electromagnetic wave can travel through vacuum. Okay, it can travel through vacuum. And it travels through vacuum by actually creating a whole bunch of dipoles. Like if you have D equals to epsilon E, okay, what does this epsilon naught mean? Actually, it means that you're creating little dipoles in vacuum as it propagates. You can think of electromagnetic wave as being something that polarizes vacuum. Vacuum is nothing. How can vacuum be polarized? Well, you can think of vacuum as being consisting of electron-positron pairs. Okay, electron-positron pairs, when they add up together, they are nothing, because one is antimatter, the other is metal. Okay, so lurking in vacuum, everywhere in vacuum, there are a lot of nothingness hiding there. Those nothingness are called electron-positron pair. Okay, they are nothing. And as electromagnetic wave propagates through them, they polarize all these electron-positron pair and produces a little dipole. And then they will be next to each other. Lots of them in vacuum, next to each other. They'll be coupled to each other like the linear atomic chain. But they will be coupled to each other via Maxwell's equation. All these little dipoles will be coupled to each other. Like Maxwell's equations, then you can actually write down Maxwell's equations for the propagation of electromagnetic wave through vacuum. Okay, you have a classical picture of simple harmonic oscillators that oscillate in space. But now replace those little simple harmonic oscillators with quantum harmonic oscillators. Then you get quantum electrodynamics. Okay. You will get phonons out of this kind of system. You get photons out of this kind of system. We'll go into the mathematics and talk about the detail later on. And because we need to quantize the simple harmonic oscillations, you have to learn about the quantization of a very simple harmonic oscillator, which is this one. This is very simple. This is a classical picture, but then when you replace it with a quantum picture, this is what you have. Okay? All the energy levels that you have here is quantized. Okay, we'll see how we do that in the next lecture as to how to quantize electromagnetic field. Okay, yes?
I'm just curious, in vacuum, what is the carrier of these plus and minus charge?
Nobody knows. Okay, nobody knows. There are a lot of contradictions about the existence of electron-positron pair. Means that there will be infinitely many of them.
It's not really vacuum.
Vacuum is not really vacuum. There's something in there. And that's why we have this vacuum fluctuation. And this has been always a point of debate. When you're at the ground state, okay, there's still some energy left. And what does this energy mean? Because we see that this ground state looks something like this. Okay? And it has zero mean, this oscillation. You can think of this as a harmonic oscillator. Okay, in this very ground state. It has zero mean. Okay? But then its variance is not zero. That means that there's some energy associated with this oscillation that has non-zero variance. If you take a square and try to average it, it doesn't average to zero. It means that it has some energy associated with it. And that energy is this 0 point energy. That if you have an oscillator that oscillates, it has zero mean energy. Its mean of its square is not zero. Okay, and this is called vacuum fluctuation. Some people believe it, some people don't. If you believe the mathematics, then it's there. If you believe the mathematics, it's not there. So people are still debating this energy if it is there.